Alright, should be becoming live anyway, very soon, yeah, very shortly, any minute now. So, yes, this is a draft, physics.com, debatephysics.com, also video presentation. And, yes, just more arguments. So, today I saw a video and I thought, oh, great, nice piece of evidence, sliding block kind of video with rubber bands. But then I did the frame rate thing, and again, it's really kind of mushy. Depending on how you count the frames, you can get 1.45 to 0.7, in terms of, because somebody's not really releasing the two objects at the same time, no quick release or anything like that. So anyway, it was just kind of disappointing that, this can't get resolved. Now, I will go through all the reasons why I'm confident. There just can't be, there's no possibility that this silly theory, that you square the velocity, it makes more energy, can in any way be true. And I'd argue it goes all the way to elemental thermodynamics, that the whole idea of thermodynamics breaks down if you can create free energy by merely transferring energy from heavy things to light things. You can just make tons and tons and tons of free energy. Just ridiculous as a concept. And I certainly know that gravity is collected in units of time, not in units of distance. That's Galileo and Newton, and it's really solid physics. It's really easy to draw it and understand it, so I'll draw it to understand it again and again and again and again and again, if that's what it takes. Alright, so I did find this video, which just shows a spring oscillating, and I thought, okay, well, this is so close to, what the hell did it just do? Screw everything up? No, everything's okay. Alright, so, it's really close to the idea of the suspended balance, the lever in the air. So I guess I might as well do that. Let's see, we don't need this. What is that on for? I don't know. Don't need that at this moment. The simple thing that I actually did make one of these experiments, for my own satisfaction. And I used little weights that were stuck together with magnets. So I could do a 4-to-1 relationship, 4 times the distance, and so you have a 4 mass going 1 velocity, and over here you have a 1 mass going 4 velocity. And it creates this kind of silly circumstance where basically the claim is that there's 4 times the energy moving on this side than there is on this side because of the squared velocity. And obviously the momentums read exactly the same. 4 times 1, 1 times 4, same thing. So it makes perfectly good sense that it balances and it oscillates perfectly. So again, this oscillates 1 unit of distance. At the same time, this oscillates 4 units of distance. Kind of easy to understand. This is 4 times the velocity. This is 1 time the velocity. And the trick is that the energy has nothing to do with this object or this object. They're always the same weight. So technically, they would always stay in any position you put them in. They're not fighting each other. And all that really happens is the lever itself, at that critical point where the lever pushes to one side to the other, that's what's really happening, is that mass is actually going from one side of the lever. It's being thrown onto the side of the lever that's going up. So when a part of the lever goes up, it actually gets heavier. And that's why it stops and then goes back down, is because it actually got heavier on that side. And when the other side goes up, it starts getting heavier and it goes up. So it constantly has negative feedback, you could argue. So there's a little bit of negative feedback, and the mass is essentially just jumping from one side of the lever. This little tiny bit of mass just switches from this side back over to this side, and that's what's oscillating, is that little bit of mass back and forth, back and forth. Well, anyway, and so the point is that it demonstrates that it takes the same energy to do this that it takes to do that, The lever itself would also do the same thing if I didn't have any masses on it at all. So, I mean, it's clear. It's a pretty clear description of the equality and the function. Okay, momentum works. Kinetic energy makes no sense at all. There can't be, I can't have an oscillator, that is, where the same energy is causing the effect. I can't have an oscillator that has 4 times the energy on one side of the oscillation. You can't do that. I mean, that should be something everybody agrees with, that, yeah, that can't really happen. So there's got to be something else going on here. They have to explain. And, yeah, of course, they don't explain nothing. They just say, Leibniz says so. You know, that's all they know how to say. Leibniz says so. Because it's not what Newton said. You know, they keep lying that this somehow is Newton's physics, but obviously it's not. All right, so in this other experiment, so that's pretty much, you would argue, a harmonic oscillator. I mean, it works fine, oscillates 100 times, demonstrates the point. So this other one you can do is you can take a spring, and you can do this. So the rules are basically this can be done horizontally or vertically, and it will produce effectively the same results. So there's no rule against, you can either hang it or you can slide it back and forth, and all you have to do is frictionless. Now obviously going back and forth across the surface isn't going to be frictionless unless you got like air cars or something. Like on an air track, somebody should do this experiment with an air track, I guess. Would be sort of the argument, to attach a rubber band, you know, and allow the cart to move back and forth between 2 rubber bands even. But regardless, so the point is you have a spring which has a natural length. You add a mass to it, okay, and create a new length with a mass, okay, and you know, all you do is put in, now you can just put in energy like the lever. You put in a little bit of energy, you'll get oscillation back and forth, and if you put in 2 units of, you know, energy, you're going to get twice the velocity. So the period will always stay the same. So if I put in, so if I stretch it 3 times, I'll get 3 times the displacement up and down, and it'll happen 3 times faster. So there'll be a perfect correlation between how much stretching and how much velocity. So kind of proving Hooke's law, I guess this is basically the standard proof for Hooke's law, that you know, and the trick is that the weight is always attached to the spring. So in the case where people are launching things with springs, as pointed out, the big failure here is that the faster you're trying to make the spring go faster, okay, to launch something lighter, and going faster, it doesn't like doing faster. You know, so it's less efficient the faster it has to move. So the faster it's moving when the object leaves, and it leaves the spring, that means the spring itself is moving that fast. And so obviously all of that energy going that fast is still in the spring. So the spring wobbles a lot more. So the faster the spring's going when the thing flies off, the more the spring's going to wobble. And the slower the spring's going when the thing leaves, the less the spring wobbles. So obviously the less energy is still trapped in the spring. And so that what ruins these experiments where you're pushing or pulling something with an elastic, is that it's sort of defeated by the fact that the elastic doesn't stay compressed. So I guess a way to do this with a constant, but that would be a constant acceleration. I'm just trying to think of some way that you could defeat this problem, but you know, I don't think you can, except to, you know, so it's worth just thinking about. So let me redraw this. So if I was to do a sliding block and I didn't allow the block to get up to its peak velocity, and I just measured it based on its acceleration, then it couldn't possibly, I guess, waste any energy. But still, there's still a limitation to how fast a spring can move. So that's the other part of this. See, this spring can only go so fast, right? So if I have a spring it has a speed that it can move. All right, so this is a stiff spring. You know, it's kind of got a high constant, so it can move really fast. But we know that some springs, especially things like rubber bands, they're kind of, you know, they don't move very fast. You know, so I could take this rubber band, and you know, maybe I could measure the speed that it goes, but it's not very fast. If I, you know, I could probably film that, and you know, it would show that it's not very fast. It's not nearly as stiff as this spring in terms of how fast it's capable of moving. So that's part of your limitations. You always have to realize if you're trying to move something and the rubber band can't go fast enough, you're not going to get much energy into your object that you're trying to move if it's very light, because your rubber band just doesn't go faster and faster. So it's going to be defeated. So what I was thinking though is if you could put a barrier to ensure that the rubber band never stops pushing on the object. So say if the rubber band had a natural length here, all right, then if you were always stretching it, so if you stretched it to here, you know, all the way from here to here, and the natural give up point would be here on this side of the stick, then at least it would never stop accelerating the object. And so you might be able to get a better description of twice the velocity using 2 rubber bands versus say 1 rubber band in the other case. But you're still going twice the velocity, so the problem is you still need the rubber band to move twice as fast, which it just might not be able to do. So that's the limitation. So yeah, it would be better if we could do these experiments with air pressure, you know, or some other mechanism, but all of those have their complications too. So the problem with air pressure is you have cylinders and valves and all that kind of stuff, and you know, it's you can't just have any old syringe and have it move at speeds too, because of the friction it creates to create the vacuum you need. You know, you need the syringe to be blocking all the air in the cylinder, so there has to be quite a lot of friction there. So that sort of defeats that kind of experiment also. So yeah, so that is the irritating part. All right, so anyway, so let's do this video thing, and so it's just, to me, this is just like the suspended balance in terms of it's just demonstrating that momentum does make perfectly good sense, and that kinetic energy in this circumstance doesn't make any sense.
Important parameter is the amplitude of the motion. In order to determine the amplitude, you have to first figure out where the equilibrium position is. And that's the position at which this mass is not moving at all. So it looks to be at about 19 centimeters from the support up here.
Right, so we know that twice the mass, if I put twice the mass on it, will go way, way down. So we're really only going to put in a small amount of force. So the only force he's going to add is, like, say if this was 100 grams, he's just going to add 110. So he'll add 10 more grams of weight. Either way, pulling down or raising it up. And the bottom line, though, is for each amount of distance, there will be twice the velocity, because the period would always remain the same. So the period of the oscillation will be exactly the same, and obviously through very different ranges of velocities. So obviously, this is again just a proof of Hooke's law, but I mean, it's just basically showing that the amount of deflection in the spring is completely correlates to the amount of energy, velocity, mass times velocity.
The amplitude is defined as the distance between the equilibrium position, and I'm talking here about the top of the brass cylinder here, where it meets the meter stick here at about 19 centimeters. The amplitude is defined as the amount of...
So there's just no way of getting around the fact that you're going to have a certain distance, a certain amount of extra energy. You're going to put in a little, you're going to give the weight a little extra weight, and then you're going to release it. Okay. So you're basically giving it the weight and then taking the weight away. And now it's going to be buoyant and bounce and that. And the simple argument is no matter what weight I put in, 10, then I put in 20, and then release and then let the 20 off, I'm going to get twice the velocity. And if it's 30, I'm going to get 3 times the velocity, proving that, again, it's momentum based.
Dispersion from the equilibrium position. So to create an amplitude, a motion with an amplitude of 1 centimeter, I'm going to want to move this mass 1 centimeter up and release it. And so now it's oscillating roughly between 18 centimeters and 20 centimeters. I could have done the same thing by moving it down to 20 centimeters, and then the overall motion is still 2 centimeters from top to bottom, but only 1 centimeter between the equilibrium position and one of the maximum positions. So now we want to look at the dependence of the period on the mass and the spring constant, and also the amplitude. First the amplitude, and in order to just get a rough idea.
It's kind of funny, the 2 pi kind of thing, because frankly, it's just a number. So why don't they just solve for 2 pi? Well, it's 2 pi. Why don't they just put the constant in? It's just sort of interesting that it's a 6 number again, sort of like the gravitational constant. It's a 6, 6, and in this case, I guess 6 to 6.3, right? 6.3.
About how the period depends on amplitude. And let me look at a couple of different amplitudes. Here's a fairly small amplitude. Boom, 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 boom. Here's a medium amplitude. Boom, 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 boom. And here's a large one. Boom, 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 boom.
Right, so proving the point that no matter what amplitude I give it, it's always the same period, meaning the velocity is completely correlated to the amount of distance. And so it's a momentum equation.
And back to the small one again, and we're just getting a rough measurement here. Boom, boom, boom. I think you can tell the amplitude, or the period doesn't seem to be depending much, if at all, on the amplitude. And in fact, the mathematics bears this out.
So that's probably all we need from the video, frankly. That's the rest of it is just him going over the formula in nauseam kind of thing. He does put a double spring, but it's with a different weight, so it just kind of defeats the whole purpose. So it doesn't demonstrate much, except obviously double the spring is going to half the amplitude, and so it will change the velocity by a half. But that, like I said, their side already concedes that apparently that you can change masses. You just can't change. Well, you can change masses in all these experiments except the lever, where even when you have a 1 mass, somehow the 1 mass doesn't obey conservation of momentum, and you can destroy the momentum, which doesn't make any sense at all. All right, so I guess that's it for that, and the rest, will just be me doing the same old crap, I guess, because there's not much else to do until we get these better experiments. And that's the part I have to figure out, is what's the best experiment. Now, obviously, I argue the lever launcher is a good one, just because it's immune to any problems with the elastic device you're using. Can't fail, because you're going to move the lever exactly the same speed. And so if you move the lever the same speed, you don't have to worry about the fact that the spring loses efficiency the faster you make it move. That the spring has a very finite maximum velocity, and that fact won't get in the way if you're moving the lever exactly the same speed in all the experiments. Then you don't have to worry about that. So I've got to say that that's got to be the best way to do these experiments. Now, what has been done, I mean, the Brozo did do the experiment, and it did get results very distant from what is claimed by the aggressive naysayers, opposing my arguments. The people who think this 1/2 mv squared has some sort of credibility. The people who think, like I said, let's just draw it up here again, just to be clear what these wackos, these silly people are saying. They're saying it takes 25 times the fuel, the force, 25 times the force, to go 5 times the velocity. That's their assertion about reality. And the vice versa part, that 5 times the velocity will equal 25 times the force. That'll do 25 times the work. And it's ridiculous. It doesn't happen. You can't get 25 times the work out of a water wheel if you make it go twice as fast. As I pointed out, I think everybody knows a generator doesn't work that way. I run a generator twice as fast. I'm just going to get twice the watts. I'm not going to get 4 times. And if I run it 3 times as fast, I'm not going to get 9 times the watts. None of that's going to happen. So it really is just bullshit. It just doesn't. The real world doesn't work that way. The real thing was always momentum. That's what Newton said kind of clearly. Twice the force, twice the velocity, 3 times the force, 3 times the velocity. And, unfortunately, it's finding experiments that verify that. That's the tricky part. Because of the fact that all these ways you can push things aren't ideal in terms of guaranteeing the creation of the velocity required. Now, the one that should work, this one hasn't even been tested either, frankly. I haven't seen anyone actually prove, this one. But, the idea of a ramp, and shooting something off a ramp, and that this height should guarantee you, a velocity. So, the height will be proportional to the velocity because of gravity, and that you'll get your mgh value, on the ramp as a rolling velocity. Now the question is that true? Because the fact is that it will have a bunch of angular rotation, and so we know it rolls at different speeds depending on where I put the mass. If the mass is on the outside of the object, it'll roll a lot slower than if the mass is on the inside, near the center of rotation. It'll roll much easier, and it will complete the task of rolling quicker. Now, what speed it'll be going when it finishes is the question. So the acceleration will be at a different rate because there'll be a different proportion of the acceleration converted into the portion that's going to be in the rotational angular motion. So if we can make them slide instead of roll, then they should fall at the same rate. So that would be an interesting way to do it. But regardless, let's just say that for the sake of argument, 4 times the height will get you 4 times the velocity. Twice the velocity, which is what we're after. Then clearly they're going to argue that twice the velocity is 4 times the energy. But obviously, if I do launch with twice the velocity, it's just going to go twice the distance. It's not going to do anything else because I'm not taking the energy out. So that won't prove anything at all. Yeah, so that won't work. That won't do any good. So we have to have twice the velocity So we'll know we'll have twice the velocity when this flies off the end here, gets to a, so again, it's just basically we have to have it hit something that we can depend on. And yes, you can depend on collecting with a spring, you just can't release with a spring. So frankly, we should be able to measure it with a scale. So you should be able to do this into a scale, you know, just do this dropping thing from 1 unit of height and 4 units of height, and you should be able to detect twice the velocity should be twice the compression of the spring. And so that's doable, I guess. Yeah. But it's always just better if we could just find some way to measure how fast something's going, and then just do the experiment with a timing gate, and just, you know, do the experiment lots of times, and just to wait for the one that's twice the speed by, you know, just by chance. You've got it at the right speed. That would be the easiest way, I think. Simplest. Yeah, would be my choice. Alright, so yeah, I haven't advanced. It's still stuck just trying to think of these different ways to do the experiment where you can get rid of friction and, the liabilities of not very good elastic objects. I mean, elastic objects that aren't elastic over a very large range of velocities. So that's sort of the downside, is the problem of pushing something with something that isn't capable of producing the proportional amount of velocity. So yeah. Alright, so I'll just do the real quick argument about gravity and then get out of here. Just to verify why I am so confident and why I know, I know what they're arguing isn't true. Okay, and I know it for this very good reason. Alright, so something falls in gravity, and it falls this 1 unit of distance, and that's going to be 1 unit of time in both of these experiments. So these are the same masses. So this one's being dropped from 4 times the height. Alright. So, and there's no doubt about what's going to happen, in terms of this experiment. There'll be a certain unit of time. Now, we could make this, so this is 1 second, and this is 4.9 meters of distance. And it'd be going 9.8. So we could say all that. So we could say it hits the ground going 9.8 meters per second as the velocity. Per second, not per second squared. It will travel 4.9 meters in doing that. And that'll be exactly this, 1 second. So it'll be 1 second of time. So this will be 1 second. Alright, and this is going to be 1 second. And do exactly the same thing, 4.9. And it'll be going 9.8. Alright, so that's what you know. That's what you're starting with. And then you absolutely know that if I turned off the gravity, I'm going to get these two things will already happen. This 4.9 and this 4.9 are the 9.8 I have here. That's my velocity. I've already got it. So I'm going to travel this 9.8 without any, even if gravity was off. That's how far I'll be right here. If gravity turns off, I'd be right here, because that's the velocity I've gotten. So this doesn't require any, I don't need any extra force to do this part of the voyage. And the only thing I'm going to get in this next 1 second, so this whole thing will be 1 second. This whole bit here will be 1 second. So it's 1 second to do this, 1 second to do 3 times that. 3 times. And the only thing I'm going to get is this. I'm going to get this. This will be the only thing I get in that second. I'll get the 4.9, same thing I got in the first second, and I'll get the extra 9.8 added, so now I'm at 19.6. So we know this is all time dependency. This is twice the velocity. Okay, it's twice the time. It's twice the weight. It's twice the force. It's twice everything. It's not 4 times anything. There's no 4 times anything there. I didn't collect 4 units of energy. I didn't collect 4 units of gravity. I only collected 2. because gravity isn't 9.8 meters per second squared. It's 9.8 meters per second over 1 second. That's what it is. All right, you don't sit there and take this second and multiply them times each other. This is 1 second. This is 1 second. Okay, you can't multiply them times each other and call it second squared. It's just wrong. Yeah, it's absolutely wrong. 1 second times 1 second is 1 second. It is not second squared. All right. So that's why I'm confident. It's because I know that's correct. I know that's how Newton understood it, and that's how Galileo understood it, and they didn't believe any of this mush. I mean, this is an amazing thing to assert. And to think that Newton wouldn't mention it anywhere in his entire, arguments about all of the physical dynamics, like nowhere he mentioned this tremendous capacity to increase energy this way. It's ridiculous to say this is Newton's physics. It's not Newton's physics. It's Leibniz's physics. It was argued for 100 years. Unfortunately, they didn't have any good experiments 300 years ago, and they still don't have any good experiments now. So that's the part that's just really disappointing. And I guess it's going to be up to me to try to do the experiments, but because there aren't any other honest players looking for the truth. But I'm just confident from life experience that I know, I'm not going to get 25 times the light out of a light bulb by putting 5 times the force in. Ain't going to happen. 5 times the electricity isn't going to get me 25 times the photons. That crap doesn't happen. Alright, being it there's no chatters and it's late and I still don't feel good. Yeah, it's been a rough, this whole quitting the nicotine thing. It's just been like 2.5 weeks now. It's just, yuck. I mean, I still ain't free of it. It irritates me. I'm not right anyway. There's something else fucked up. Something blood sugar or something. But anyway, just isn't the best of times. Let's just leave it there. It's not the best of times. Alright, so I'll see if I can find some other experiment somewhere. But I'm just saying that all these little experiments do add up to a pretty convincing argument. I mean, the balance says momentum is conserved. You really can't not conserve the momentum, and you can't have any notion that there's a bunch of free energy on one side, that somehow one side of the oscillator has 4 times the energy. That's a ludicrous argument. And again, the oscillating spring is saying the same thing. It'll sit there and oscillate 50 times or 100 times, and it's basically saying that twice the input force, twice the velocity, and that's it. Not 4 times the velocity. Not anything. No evidence that it's 4 times the energy. It's just twice the velocity, twice the momentum, twice the energy, twice the work, twice the force, twice. Alright, so till the next time and such and so forth and whatnot. Yeah, that's enough. Yeah. Yeah, just I'm tired. It's just a fact. So till the next time and such and so forth.